Now that you are familiar with the expected value of a random variable, we turn our attention to something a little bit more complicated, the expected value of a function. To motivate this, consider a little dice game. You roll an ordinary six-sided die. If you roll a 6, you win $10. Any other number pays out 0. And there's a $2 charge to play this game. So what is the average profit or loss? To answer this, we can define a random variable W. This is the amount you win. So if you roll a 6, your winnings are $10 minus your $2 entry fee, so $8. If you roll any number from 1 to 5, the winnings are $0 minus your $2 entry fee, so you lose $2. The expected value, or average profit loss, is given by the formula for expectation. Plugging in the numbers that have been given here, you find that on average, you are going to lose 33 cents. Let's write this in a different form. How about letting x be the number that is rolled? Then everything that was just written can be rewritten in terms of x. If you roll x equals 6, then the amount you win, we'll call it f of x, is $8. If you roll any number x between 1 and 5, the amount you win will be negative $2. The expected value of w, the winnings, can be written as the expected value of f of x. Recall again that f of x is the amount you win if you roll the value x. So our earlier discussion of a dice game has allowed us to develop a new formula. The new formula takes a variable, like the number you roll, and it determines the average value of something else that depends on it. In this case, the average value of your payout. So that formula is going to be used as we go forward. This is known as the expected value of a function. So let's look back at the example that was just covered. X, the number we roll on the die, had a PDF given by probability x equals 1 is a sixth, 2 is a sixth, and so on. The payout function gave the value of 8 when the input or the roll was a 6. It gave the value of negative 2 when the input value was anything from 1 to 5. Now we have all that is needed to compute the expected value of the function, the payout. So start with the formula for expected value. The formula says take the probability at 1 times f of 1. Probability at 1 was a sixth. Probability of 2 times the payout at 2, and so on. Plugging in all the values, they were all, in this case, 1/6 for probabilities, and the various payouts, again, gives the answer that the expected payout is negative 33 cents. Let's turn to a more traditional example. We've thrown out the dice, we just have a random variable x. It can take on 4 different values, and the probabilities are given here. This time, I'll look at the average value of x squared. So that means in our expected value of a function formula, my function will be x squared. Take the formula for expected value of a function. Replace f of k with k squared. Again, k is just the quantity we use in our summation. It represents specific values that x may take. And then write that out. So the 4 values x could take were negative 2, negative 1, 0, and 1. Plug in the values for the PDF, square as needed, and you get the expected value of the square is 1.8. One little detail to keep attention to is notice that the function that we multiply here is never applied to probabilities. One of the most common mistakes when students compute the expected value of a function is to plug in the probability. For example, in this case, a student might take 0.35 squared. That's wrong. Anytime you find yourself manipulating probabilities, you're probably making a mistake.